Hello everybody, my name is Tyler Lay. Welcome back to another great day to talk about concrete. Today in our video, we're going to talk about some of the basic terminology of concrete. You're going to learn how to talk concrete with the best of them, right? You'll be able to talk to a concrete guru after today's video. Also, we're going to learn some mechanical properties of concrete. Okay, what's it good at? What it's not good at? Things like that. We're going to start today with a question. What is the difference between concrete and cement? Ooh, a puzzling question. You've probably heard lots and lots of people say, oh, there's a cement truck. Or they'll say, oh, the cement driveway, or the favorite of all, the Beverly Hillbillies. Man, that's an old school reference. Used to say the cement pond. None of those things are true. We don't make things out of cement, at least not infrastructure that people use every day. Sometimes we'll make oil well plugs. Okay, this is where they actually pump cement and water down an oil well to help plug up the well before they start to pull the oil out. That's about the only time we use cement and water together. It's called paste. We're going to learn all about these crazy terms today. Let's start with that question again. What is the difference between concrete and cement? Well, cement is to concrete as flour is to bread. Cement is one of the ingredients inside concrete. It's a really, really important ingredient. It happens to be the most expensive ingredient, but durable structures are not made by only using cement and water. And to make a durable structure, you're going to need to add aggregates. Why is that? Well, aggregates do lots of good stuff. One thing that they do is they restrain shrinkage. We're going to learn about that. It'll be the future, but it restrains shrinkage. Shrinkage is where the concrete actually changes shape, or the cement paste changes shape over time, usually because changes in places where water is. And we need something to hold that back, and the aggregates do a great job of that. If I just had a big block of cement paste, that is, cement plus water, it would crack itself up. Again, those aggregates, they'll help restrain those cracks. They won't happen. They might, but they'll be on a very, very small scale. They won't be as large. Also, aggregates are way cheaper than cement. Way cheaper. So by adding it, you're diluting the material. But aggregates are pretty strong, right? Yeah, pretty strong. So you're diluting the material down, and you're getting something that's more durable. This idea where we combine two different materials together is called a composite material. It's a combination of two or more materials that work together to achieve an improvement in performance. That could be a reduction in cost. That could be an improvement in mechanical performance. Could be more sustainable. There's all kinds of good things that composite materials can do. Composite materials are very powerful. And the most used composite material on the earth is concrete, right? Because it's awesome. So what are some examples? I said Portland cement plus water plus aggregates is how we make concrete. Again, extremely popular composite material. There's also something called plywood. What's plywood? That's when you take thin sheets of wood, thin pieces, and you glue them together. And those thin pieces are from different cuts in a piece of wood. It helps keep them more dimensionally stable. What? What's that mean? It means they don't change dimensions. So we may have one piece of wood cut this way, and then we may have another piece of wood that's actually cut a different direction. The grains may go in an opposite direction, like this. And then we'll come back with another one, and then we'll come back with another one. Again, by gluing them all together, not only do you make it less expensive, but you get a better performing material. Fiber composites, another very, very popular material, composite material. That's where you take some kind of structural fibers and maybe you glue them in a fiberglass matrix to help hold them together. Again, these little bitty fibers by themselves are not that strong. The matrix is not that strong, but together, now they have pretty good strength. It's pretty cool. Now let's talk about some more terminology. This is kind of the basic words, so you can start to set the world straight. right? Because it's your job from now on to change people's minds about concrete, or to let them know that it's not cement, it's concrete. Let's talk about paste. Paste is when you take cement and you add water. That's how you get paste. When I call something paste, and I'm talking about concrete, that's what I'm talking about. It's like the glue that holds everything together. That's why it's called paste. Now let's talk about the next one. If I add something to this, if I take my cement and I add water to it, and I add one more thing, if I add sand to that, then I get a grout. And sand is also known as, in this class, sometimes, or in this video, we'll sometimes call sand something called fine aggregate. Oh my gosh, misspelled aggregate. Fine aggregate. Now, to make concrete though, we need one more ingredient. We need cement or some kind of binder. We need water. We need sand. And we need something called stone or gravel, or you might call them rocks. And the fancy term for rocks is something called coarse aggregate. Fine aggregate, that's the small stuff. Coarse aggregate, that's the big stuff. And admixtures, oh man, we use a lot of admixtures. That's anything else you throw in the mix. Okay, that's all the herbs and spices that help really give it cool new properties. Okay, admixtures are really exciting. We'll talk about them coming up. They may be chemicals you add, or they may be minerals. This is more like powders that you add. Okay, and these are both kind of mislabeled names because pretty much anything you add is made up of a chemical, and a lot of things you add may be a mineral, and heck, even minerals have chemicals in them. But historically, we've called them either chemical admixtures or mineral admixtures. And again, we'll talk more about those coming up. Next, let's talk more about the aggregates. We said fine aggregate and coarse aggregate. We said fine aggregate's the sand and coarse aggregate's the larger stuff. Let's get a little bit more specific about that. Fine aggregate. That's aggregate smaller than a number 4 sieve. Wow. What's that? What's a sieve? Well, sieve is a screen with certain size openings in it. But what's a number 4 sieve mean? Well, that means 4 openings per inch. 4 openings per inch. And the size of those, each one of those openings is about 0.2 inches. Okay? About. That's fine aggregate. So everything that goes through that sieve would be considered a fine aggregate. Let's talk about coarse aggregate. That's aggregate larger than a number 4 sieve. That means everything that would maybe be caught on this sieve would be considered a coarse aggregate. And we may have different sizes, and it's typical to talk about different sizes of aggregates. We'll talk more about that later. Typically, though, our rocks are anywhere from, our coarse aggregates, anywhere from this about 0.2 inch to typical max size is about pardon me, is about 1 inch. Typical maximum size is typically about 1 inch. But however, sometimes we do use larger rocks. Depends on the application, especially in dams. They'll use very, very large rocks sometimes in those structures. Now, we've moved on, we've moved past the rocks, and actually about 80% of the volume in concrete, 70 to 80% of the volume in concrete is made out of aggregates, right? It's crazy, right? What's about water? Water's pretty important. Water's what reacts with the cement. The water must be clean and free of chlorides. Here's why. Chlorides attack your steel. They cause corrosion. Got to watch out for them. You don't want them in your water. You don't want to begin with chlorides already inside your concrete. That'd be bad. Typically, any potable water source can be used. What's potable mean? That means you can drink it. If you can drink it, then you can use it for concrete. Now, there are some non-potable water sources that are out there, and you'll have to check your local specifications to see what people allow and don't allow. Now, we have to watch out for concrete. Sometimes we have other ingredients like fibers. That fibers help hold the concrete together if it cracks, and they're becoming more and more popular. They're used as reinforcement. So we don't always have to use rebar. Sometimes you can use fibers, or you can use both, rebar and fibers together. It's pretty cool. There's two main types of fibers that we use in concrete. We use polypropylene fibers. Those are like really, really flexible plastic fibers. And they're helped in the fresh state, right? Actually, right as the concrete's hardening, right as it's setting, right as it's gaining strength, really early in its age. And then we'll use steel fibers. But there's also hard plastic fibers. So there's steel and hard plastic fibers. And these will help in the hardened state. These help if a crack starts to form. The idea is these fibers help stitch the crack together. So if a crack forms, and if you had a fiber going across the crack, okay, it would keep that crack small. It would keep that crack from becoming too large. Let's talk about classes of concrete. And one good way to talk about them, people sometimes call it weight, but it's a much better term is density. This is the density. This is the weight of the material per volume, okay? So when we talk about lightweight concrete, we say, why would you ever use lightweight concrete? Well, if you had a structure and you wanted to reduce the weight, sometimes the initial weight of the concrete, the dead load is what they call it, can be extremely high. And if you can reduce that, you can use a more economical structure. So typical lightweight concrete, you're going to want the density to be less than 110 pounds per cubic foot. So if you could think of that in metric terms, that's 1760 kilograms per cubic meter. Our normal weight concrete is somewhere between 145 to 150 pounds per cubic foot. So a typical foot of concrete, that's a foot by foot by foot of concrete, weighs somewhere between 145 and 150 pounds. And that in metric is between 2,300 and 2,400 kilograms per cubic meter. And then sometimes, very rarely, we'll get to something called heavyweight concrete. And heavyweight concrete is about anything over 195 pounds per cubic foot, or a metric equivalent of 3,100 kilograms per meter cube. So how do we change the density of concrete? Well, I told you before that about 70% of the volume is the aggregates. So that's the easiest way to change it. If you want lightweight concrete, you use lightweight aggregates. You use pumice or expanded shale, something that has air inside of it. So you're casting more air inside of your concrete. Pretty awesome, right? And if you want heavyweight concrete, then you need really, really heavy aggregates. Things like pieces of steel, okay, that you use as aggregates inside your concrete. And why would you ever need heavyweight concrete? Well, sometimes you just need a lot of weight, but commonly they use it in shielding for nuclear reactors, for x-rays sometimes. Now let's talk about strength. When people talk strength in concrete, when we talk to a normal concrete person on the street, if you could find one, say, hey, What's the strength of your concrete? Almost always, they are talking compressive strength. That's the test we talk a lot about, compressive strength. And in America, when we test compressive strength, we're testing cylinders, and there'll be a whole big lecture coming up on cylinders. And in Europe and other countries, they often test cubes. Okay? Cubes made out of concrete that they load until they break. And they load them like this, and like this, and like this, and like this. Don't worry. A lot more coming on that. So if we have something called a low strength concrete, this is, kind of lower strength. We would say something like less than 3,000 PSI would be a pretty low strength concrete. And if we talk about the metric equivalent, that's less than about 20 MPa. And if we talk moderate strength concrete, that's somewhere between 3,000 and 6,000 PSI. And again, if we talk in the metric equivalent, that's somewhere between 20 to 40 MPa. And high strength concrete, it's tough to pick a number here, but just a good estimate is anything about over 6,000 PSI. This is not an official definition, but anything about greater than 6,000 PSI is higher strength concrete, and that's greater than 40 MPa. And we're going to find later on that actually the key to the strength of concrete, or one of the main keys, there's several of them, but one of the main keys is the water to cement ratio. And we call it the WCM. This is, W stands for water, CM stands for cement or cementitious, binder. Okay? Water to cementitious ratio. And this value, to get this range, is somewhere between a 0.4 to a 0.6 water to cement ratio. Now, historically, people have always talked about strength as being the main measure of quality for concrete. And for a long time, that's right. It was. But things have changed a lot. We've got a lot better tests out there besides strength, because things can be super strong, but if they're not durable, or if they're not constructible, they're not that useful to us. We need all of these things. Durable, constructible, and strong. At least strong enough. Don't worry. Talk more about that coming up. So, compressive strength is not the only strength that we measure or care about. There's other ones that we do measure. One of them, but compressive strength, though, if we picked a concrete that had a compressive strength of about 4,000 PSI, and that's kind of a middle of the road, maybe a little bit lower strength than what we would typically see today, but that happens. And if we were to, and again, the way we would measure that is we would take something like a cylinder or a cube, and we would load it like that. And if we were going to try to measure the tensile strength, one thing that we would use, one thing I forgot to bring up is this is often called something called FC. FC, that usually means the compressive strength of concrete. And if we're going to look for the tensile strength, usually the tensile strength is about 10% of the compression strength. So this is like an equation. 10% of the compressive strength is equal to the tension strength. So we would say that's around 400 PSI. Oh yeah, I forgot my metric. This is the same thing as about 28 MPa. This is the same thing as 2.8 MPa. And then when it comes to flexural capacity, an equation that oftentimes people found to be useful is that if I have the compressive strength, then the flexural strength is equal to 7.5 times the square root. Yeah, that's right. The square root of the compressive strength, which is equal to about 475 PSI in this case. That does not mean the flexural strength of concrete will always be 475 PSI. But in this case, with 4,000 PSI concrete, A good estimate would be that. Or that's equal to 3.3 MPa. Right, so how would you measure these things? Well, with tensile strength, you would take one of these cylinders and you would pull on it. Not a very easy test to do. That's why very few people do it. And if you wanted to measure flexural strength, if you had to use a cylinder, people oftentimes use beams to do this, but you could take a member and you would load it down the middle. Again, like I said, oftentimes people would use beams to measure the flexural strength. That's because it has a uniform cross-section. And they would load it like that. And then the last one we're going to talk about today is the shear strength. And the shear strength is equal to, at least the equation is, 4 times the square root of F prime C. Or another way to say it, another estimate is about 0.6 times the tensile strength. And these numbers come out to be about 250 psi, which actually comes out to be about 1.7 MPa. And you'd say, well, what's the shear strength? Well, that's when these beams, that's when these members fail, but they don't fail down here. The shear would be if they failed something like this. Flexure would be if they fell down at the bottom. So as we can see from all this, concrete is weak in tension and it's strong in compression. So we should try to use it where it's strong, right? And if we find out it's going to be in tension somewhere, we just need to make sure we have reinforcing there to hold together once it cracks. Let's talk about one more thing. Let's talk about, I've got something titled actual performance, and I have this very fancy plot shown here. And what this is saying is that in real structures, oftentimes, we don't have little cylinders that are in pure compression or pure tension. We don't have that. We're not that lucky. It's more complicated than that. And you have to look at combinations of stresses. What this plot's trying to show you and prove to you is that if I have this element, this little single element, you can think of it as a piece of a much, much larger structure. And on one axis, it's the load on one face, and on another axis, it's the load on another face. So you could call this axis number 1, you could call this axis number 2, we could call this load number 1, we could call this load number 2. What this says that if I have pure compression, if I'm on this line, I have no tension at all, no tension and no load in any other direction, it's going to fail at 1.0. That's the crushing strength of the material. And then look, in tension, it's going to fail at about 0.1, 10%. That's pure tension. But it's kind of interesting that the allowable stress, this outside ring here is the allowable load that you can put on the actual concrete before it breaks. That if I put maybe 40% of the crush load in one direction, and then I start loading it, so I put 40% in this direction, 40% in this direction. I was right the first time. 40% in this direction. And I keep loading it the other direction, then I'm actually going to go a higher strength. I can get 20% higher strength. Wow, that's crazy. You can get a higher strength by preloading it in one direction. But let's look at the bad news. If I even pull a little bit, let's say half the tensile strength, it'd be like 0.05 of the compression strength in one direction, that my strength drops greatly. If I go down this line here, I'd only be able to take 0.6 of my compressive strength before it breaks. Isn't that crazy? The whole point, the whole takeaway from this plot is that in real life, our structures are loaded in way different ways than these perfect, ideal cylinders. However, These cylinders or specimens do give us insight to how these much larger structures are going to form. Thanks for being here today. Appreciate it. Take care.